So welcome back to deploying models. So we're going to continue on the saving and deploying on train model. So this is for the topic, saving and deploying train models. So to continue the story of TensorFlow Keras, we can actually save the architecture and not just save the weights and the losses, etc. So the model configuration or the architecture specifies the configuration of the layers, how many layers there are, how those layers are connected to each other. So the weights, when we save the weights, we actually just saving the numeric values. It doesn't contain the configuration or how the layers are connected to each other. So if you want that information, you need to have the model configuration or the architecture saved. Now, if you have the configuration of the model, then the model can be created with a freshly initialized state for the weights and with no compilation information. So the API calls are basically the get config and from config calls. Now, if you want to support JSON file for saving it, then you call the model to JSON or model from JSON. And to continue on, we can also just save the weights without the configuration. So if you choose to only save the model weights, this can be useful. For example, if you have the code and you just want to retrieve the model and just build it from the weights alone, you can do this and you do not need to restart the training. So you don't need the compiler information or the optimizer state. You just want the frozen model, right? You don't update it anymore. So you don't need those additional information. Or you want to do transfer learning, in which case you would freeze these layers and you would add to it. So doesn't require you to have information other than the weights and if you have the code for the configuration of the model. Now weights can be copied between different objects by using get weights and set weights. So you can actually do this as well. But this is to save the weights into a file. This is for programs for copying the weights into a different array. Now, when you actually want to save the weights, you have a choice of two formats. You can save it as a TensorFlow checkpoint format, or you can store it in the H5 format, HDF5 format. The default format is TensorFlow checkpoint. And there are actually two ways to specify this wave format. You can save it, you can specify in save format equals to TF. And if you want the HDF5 format, you can save format equals to H5. The path argument, basically, if you also specify as ending with .h5 or .hdf5, then the HDF5 format will be used. Other suffixes will result in the TensorFlow checkpoint being used instead. So what's the difference between these two formats? So the TensorFlow checkpoint format versus the save model. The checkpoints capture the exact value of all the parameters, basically all the TensorFlow variable objects that are being used in the model. Checkpoints do not actually contain any description of the computation or how the computation is done by the model, and thus is only useful for when the source code is actually available. So if you don't have the source code, you don't know the configuration, nor do you know how to compute the weights after you've restored it from the file, then the checkpoint is not as useful. So remember, the TensorFlow save model format is the one that contains all the information. It has the losses, the optimizer, the weights, etc. So the save model format contains serialized information with the computations as well. So you don't actually need the original source code. You have everything that you need to continue using this model. And the models in this format are actually independent of source code being used to create the model. So you can actually continue using it and you can restore it fully without having the source code around. So TensorFlow will match the checkpointed values to the, this graph just shows you basically how it makes use of the checkpoint information to restore the information at different stages, right? So if you save the data, it may be at a certain stage of training. So if you want to restore it exactly back to the same state that it was when you saved it into the file, that checkpoint file actually contains information so that you can actually backtrack, go back to where it was before and save it and restore it to the exact same point in the training of the neural network so far. So this is very useful again for the purposes of continuing the training. If you have a very long training process and you're not able to complete it within, let's say, the period of time that you have, let's say for Colab, and you have only 12 hours of computation time before it will reset your session. So you need to checkpoint the data so that you can continue when you have more time allocated or more sessions available for you to use again. So the checkpoint automatically restores the state of the training to where it was when you call the checkpoint call. So it allows you to do some backtracking to the exact correct point. So this is very useful for that purpose, right? To continue your training for long periods of time. So you can checkpoint it at the end of the day, close the session. Then the next day, when you start the session again, you retrieve it from the checkpoint. Then you can basically start the training all the way from the end of the last training session, rather than starting it all the way from the beginning again. Next, we're going to take a look at the other very popular file format, which is the Open Neural Network Interchange format, which was used for TensorFlow RT. So the URL is actually here, onnx.ai. ONNX is actually an open format built to represent different machine learning models. ONNX defines the common set of operations, the building blocks of machine learning and deep learning models. So it actually, although the name is Open Neural Network Interchange, it has sufficient flexibility to also represent other machine learning algorithms, not just neural nets. And it's a common file format to enable AI developers to use models with a variety of tools, runtimes, and compilers. So you're not restricted to only one set of tools. So that's the beauty of having an open interchange format. And that actually is well supported with many different frameworks and converters. And this is just a list of popular tools from the website. So you can see Caffe2, CatBoost, Chainer, Cognitive Toolkit, which is from Microsoft. Then we have Keras, and then LibSVM, MATLAB, MXNet, PyTorch, TensorFlow down here, XGBoost, so, and even Scikit-learn. So you can see that some of these are not basically intended for deep learning, but things like XGBoost, the LibSVM, these are actually support vector machines. Sorry, this is support vector machine. This is actually a boosted tree. Two different family of machine learning algorithms from a neural network. So you can see here that basically it is quite flexible. Right? It doesn't need to be only neural networks, and it allows you to interchange between different tools. So let's say we have our safe model format in TensorFlow, and now we want to actually use TensorFlow, NVIDIA TensorRT. So we need to convert the safe model into ONNX format. So there's actually this particular library called TensorFlow to ONNX, which you can use. So TensorFlow to ONNX will actually convert the TensorFlow Keras JS, TensorFlow JS, and also TensorFlow Lite models to ONNX via command line or even via Python API. So you can convert from the safe model format into the ONNX format. So for PyTorch, it's slightly better. It doesn't require a third-party library because PyTorch actually supports ONNX internally. So all you need to do is to call the torch export function, and you will export the model into the ONNX format. So what do you do with the ONNX format? So now we want to actually do the AI inference. So of course, one way is to pass it to the NVIDIA TensorRT. Especially if it's a deep learning neural network and you have NVIDIA hardware. But what happens if you don't have NVIDIA hardware and you want to actually port it to some other hardware? So the good news is that there's actually an open runtime for ONNX, right? So not just a file format, but it's actually inference engine that reads in the ONNX format and is able to run on a variety of different hardware platforms. So you can see that you can deploy your ONNX model using runtime designed to accelerate this inferencing on different hardware. So these are just a number of different companies with hardware that can support the ONNX format. So notice that not just NVIDIA, right, which you can do with an TensorRT, but you have Intel in the picture. You also have some other more exotic companies here, right, including some from China as well. And I think this is one of the new AI accelerator chips being proposed and being created, called Habana, which actually can run in the accelerated manner using the ONNX form. And you can see that there's also this thing called the ONNX runtime, which is the open version of the runtime, so that you can port it to different hardwares. Now, to deploy ONNX with TensorFlow, you can actually call this function called the TensorFlow backend for ONNX. So this actually basically imports the ONNX file and then builds the TensorFlow graph for it, and basically the neural network for it. And then when you run the TensorFlow, it basically implements whatever it implements that particular model that's been retrieved from the ONNX file. So this is actually a bit of a reverse from the TensorFlow to ONNX. It's actually basically reads in the TensorFlow and then basically runs, reads in the ONNX file and then runs it in using the TensorFlow framework. Now, the runtime that I mentioned just now, the open runtime, you can actually find it in this HTTPS onnxruntime.ai. ONNX runtime is actually an accelerator for machine learning models that have been built and saved in the ONNX format. It is a multi-platform with a flexible interface to integrate with the hardware libraries. So ONNX runtime can be used with models from PyTorch, Keras, TensorFlow, TensorFlow Lite, scikit-learn, and other frameworks, as long as they have exported the model in the ONNX format. So notice that it is multi-operating system. You have versions running on each of the different operating systems, and it can be Python, can be C++, can be Java, or even other programming language like JavaScript. It can support different hardware architectures for the CPU. And notice that the CUDA being the NVIDIA version of the acceleration, but it can also support on the Intel 1DNN. OpenVINO is also an Intel thing, and you can see some of the other hardware libraries they provide other kinds of support, running this over the other hardwares besides the ones like CUDA. And we have a quiz time again. So again, please pause the video at the end to try to think of the answer before continuing. So which of the following is true? ONNX is only applicable to PyTorch. ONNX is not applicable to scikit-learn. ONNX is applicable to TensorFlow. Is it all of the above or none of the above? So here is another quiz question. Again, pause at the end of the video of this to think about the answer. So the TensorFlow safe model format, okay, which is the format for TensorFlow only. A, it must be in F5 format, so the H5 format. Or B, it contains the complete TensorFlow program, including the train parameters, variables, computation, and it does not require the original building source code to run. C, it contains only weight information, so the original source code must be available in order to execute the model. So D, all of the above are true, and E, none of the above are true. Again, pause and think about the answer. A, B, C, D, or E. And with that, we come to the end of this set of videos. So thank you for your attention, and I will see you in the next set of videos.